Hello, welcome to EHS Today's webcast. Protect your staff and your workplace with optoelectronic devices. It's sponsored by PILS. My name is Dave Blanchard. I'm the Editor-in-Chief and Senior Content Director of EHS Today. Before we begin, let me explain how you can participate in today's presentation. Now first, if at any time you're having audio difficulties or the slides are not advancing, simply hit your F5 key to refresh your webcast console. If you have any technical difficulties during today's session, please press the Help button on your player console and you'll get some assistance in solving whatever is bothering you or isn't working right. Most of these things are simple, so just hit that F5 key first. The webinar technology that we're using will allow you to resize the presentation. You can do that in two ways. You can either click the maximize icon or you can drag the lower right corner and that will enlarge the window. We welcome your questions during today's event. To submit your questions to today's presenter, simply type your question into the Q&A window on the left side of your screen, then hit the Submit button. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time and we'll add them to the queue. Any questions that we don't have a time to get to during the Q&A portion of the live webinar, we will forward all those questions on to the presenter and he'll be able to follow up with you offline. So again, I just want to stress, go ahead and send in your questions as many as you'd like, and all those questions will end up going to the presenter. Please also be aware that today's session is being recorded and it will be available on the EHS Today website within the next week for you to review. You'll be notified by email as soon as that archive is available. You'll also see PILS' logo on your screen. That logo is actually hot linked. So if you'd like to visit their website during the webcast, just click on that logo and a new window will open. But do not worry, this will not take you out of the webinar. And that is my housekeeping suggestions for the day. Let me now get to the more interesting part of the presentation. I'll introduce our actual speaker. Our speaker today is Thomas Hartig. He is a certified machinery safety expert working for PILS Automation Safety. Thomas has taken on many roles in his 20-plus year career with PILS, from sales engineer to sales manager to product management to safety consultant to his current position of senior technical sales engineer. And Thomas also has a degree in electrical engineering. And with that, I'm going to turn it over to Thomas. Thomas, the floor is yours.
Thank you so much for the introduction, Dave, and to all, welcome to today's webinar with the topic, Protecting Your Staff and Your Workplace with Optoelectronic Devices. This presentation will provide you an overview over these optoelectronic devices that are available today. For this presentation, we have the following objectives. There will be an introduction to optoelectronic devices, for example, light curtains. We talk about regulations and standards used for these devices, talk about the machinery life cycle, some definitions, muting, blanking, touch on safety controllers, the installation of these devices, an overview of distance calculation, an example, talk about two-dimensional safety laser scanner, validation methods and tools, and the last, a little list how to select optoelectronic devices. So the introduction to optoelectronic devices, for example, the safety light curtains. These are devices that are most commonly applied, optoelectronic devices, to safeguard personnel in the vicinity of moving machinery that have the potential to cause harm, such as presses, winders, pelletizers, and the like. Safety light curtains can be used as an alternative to mechanical barriers or other forms of traditional guarding. By reducing the need for physical guard and barriers, safety light curtain can increase the maintainability of the equipment they are guarding. The operability and efficiency of the machine can also be improved. by the use of safety light curtains, for example, allowing easier access for semi-automatic procedures. But have in mind, light curtains do not protect against flying debris out of a work cell or a machine. Now the rules and regulations. So I touched on some main ones. Of course, there are more possibly to use depending on your application, but we have the ISO 13855, positioning of safeguards with respect to the approach of speeds of the human body. We have the ISO 13857, safety distances to prevent danger zones being reached by the upper and lower limbs. Then we have the ISO 13849, which deals safety of machinery. It deals with the safety-related parts of the control system. And then we have the ICTS 62046, is safety of machinery, application of protective equipment to detect the presence of persons. Also, we have the ANSI B1119 standard performance criteria for safeguarding. Then you can also consult OSHA regulations for different machine types and additional ANSI standards or EN standards depending on your machine type and application. So for example, there are ANSI standards for robotics or for packaging machine and the like. Now coming to the types of optoelectronic devices. So there are on the market safety camera systems. Then of course we have the carbon safety light curtain. Then we have the two-dimensional safety area scanners, and also there are single beam safety light curtains available, as you can see depicted in this slide. Now the types of light curtains, so they come in different resolutions depending what you need to protect against. So 40 millimeters is the finger protection, 30 millimeters is the hand protection, and larger than 40 millimeters is for body protection. Also, those light curtains for the safety controls, there are different types. Type 2 can reach up to performance level C or SIL level calculated 1. Type 3 light curtain can reach up to PLD or SIL calculated 2. The type 4 light curtain is up to PLE or SIL calculated 3. Common features for a single safety beam light curtain, they can be cost effective. For body protection, number of beams is 1, but you can also add more. And the operating range of the sensor and the performance level or SIL rating is dependent on the manufacturer, and it's mainly used for access guarding. When we look at the two-dimensional safety laser scanner, so we have two-dimensional area monitoring. It's also suitable for applications up to PLD. It's a type 3 device, can also reach up to SIL 2. And the operating range, safety zone, warning zone, they can vary depending on the manufacturer that you choose. Also, it can vary the operating angle, the switchable safety configurations, reaction time. The protection type IP can also vary in the dimension depending on the manufacturer, but the resolution is larger than 40 millimeters, so it's for body protection, and it can provide a complete solution with the available safety controllers. Next, we have the three-dimensional safety camera system. So it's a camera head mounted over a work cell or a machine, and the viewable area, as you can see on that slide on the right, viewable area there in orange, that's dependent on the mounting height of the device from the floor or from a reference level. The zone arrangement switching is possible. It's excellent for work cell where collaboration is necessary. Reduced engineering time possibly to omit half guarding, but also here, if there is debris flying out of the work cell or machine, that's not a system to be used. It's for body protection. Can reach up to a PLD or SIL2 level. So this is a three-dimensional device that has a warning zone and a detection zone, and you can create those zones depending on the results of your risk assessment and the specific calculations on these zones. So the specific width of the warning and detection zones need to be calculated. That's an item that is good to use. For example, if your machine cell or machine itself needs to be repositioned in your workplace or on the plant floor, this unit can be moved like a light fixture with your application. Now here are some special devices, parallel light beams, safety camera systems. So this is vision in parallel, a safety camera system for press brakes. And some other technology for presence sensing. On the market now there is safety sensors with radar sensor technology. So radar technology, FMCW, means frequency modulation continuous wave, so it's in the high gigahertz range, and yes, it can can sense the human body. Also, we have available the safety mat as well. But nevertheless, these devices, they need to be considered when you're in a specific phase of your machinery life cycle. So it starts on the top, as you can see on that slide, with the risk assessment. A risk assessment derives a concept. Now, in your concept, this could be hard guarding in conjunction with movable guards or fixed guards and the like. And if these devices, the optoelectronic devices, are a way to go and bring a solution, then in that square 3 there, safety design, this is when you would specify these devices to your calculations and the like, and create your drawings. Nevertheless, for devices, we have lots of definitions, so I'm going to touch on a couple. So we have definitions of ESPE, electrosensitive protective equipment. So in standards, you find lots of abbreviations, so I'm going to go over a few of these that are commonly used. So ESPE is an assembly of devices or components working together for protective stripping or presence sensing purposes, and comprising as a minimum of a sensing device, a controlling monitoring device, output signal switching device. Here's a note. These devices can, like the ESPE, can also include secondary switching device, muting functions, stop time, performance model. So these items can get very sophisticated for use. AOPD is the active optoelectronic protective device. It's a device whose sensing function is performed by optoelectronic emitting and receiving elements, detecting the interruption of optical radiations generated within the device by an opaque object present in the specified detection zone, or for a light beam device on the axis of the light beam, so you take a light beam. We have the AOPDDR that refers to the two-dimensional safety laser scanner. It's an active optoelectronic protective device responsive to diffuse reflection. It's a device whose sensing function is performed by optoelectronic emitting and receiving element that detects the diffuse reflection of optical radiations generated within the device by an object that is present in the detection zone. And the text in 2 dimensions, and you have the laser scanner with a protection zone and a warning zone here on that slide. OSSD is the output signal switching device. It's a component of electrosensitive protective equipment connected to the machine control system, which when the sensing device is actuated during normal operation, it responds by going to the off state. So when a light curtain beams are broken, then you have a reaction on the OSSD outputs of that device. Then we have the EDM, external device monitoring. It's a device means by which the ESPE monitors the state of the control system external to the ESPE, for example, a feedback loop. Or we have a final switching device, the FSD, a component of the machine's safety-related control system that interrupts the circuit to the machine primary control element, MPCE, when the output signal device OSSD goes in the off state. And then we have the typical, the RX for receiving and the TX for transmission. We touch on response time because that's very important on these devices. The time it takes any optoelectronic device to sense an encroachment and output that signal to a safety control device via the OSSDs. The length of a light curtain affects the light curtain's response time. Then we touched early on a different resolution. So resolution R is the size of an obstacle that can be detected at any point within the protective field, resulting in an off command. Then we have the height of the protective area is the distance of the upper point of the first lens to the lower point of the last lens or beam. Cascading, host and guest, where more than one set of light curtains can be connected in series to achieve multiple protected fields and act as a single unit via the OSSD output. Here's a general description of muting. Muting is a temporary automation suspension function of safety functions by the safety-related parts of the control system. Muting shall only be provided when it is necessary for the process being performed on the machine. It shall be ensured where practical that the person cannot remain undetected in the hazard zone when muting is terminated. An external muting light will be illuminated when muting is in process. Different muting functions can be considered depending on the applications. So here you have a conveyor belt and a pallet with boxes going through muting sensors being detected, and while the package goes through, the safety function of the light curtain is suspended until the package reaches the other side and passes those muting sensors as well. Now here, touch quickly on two muting types, so types with 4 beams. It's also called sequential muting, which has 4 muting sensors. Where the packages passes through the first 2, the light curtain gets suspended, then it passes the other 2, and once it leaves the last one, the light curtain will be activated again. Or you have the 2-beam cross muting, where 2 muting sensors are in a cross format, and they need to be obviously positioned right way. And the IEC TS 62064 gives excellent guidance on when and what to use and how to perform muting. Here we see that package going one way and passing through the 2 muting sensors and then deactivating the light curtain when it goes through. But nevertheless, we have to also have some attention to muting sensors. They need to be installed so that material can pass, but personnel need to be detected. Following the switching and muting sequencing cycle, avoid the possibility of manipulation of the muting system by timing, selection, installation, and controls and the like. Here we talk about blanking, and there are different types of blanking, so floating blanking and fixed blanking. So blanking is the means of bypassing a portion of the sensing field of a present sensing device. Different types of blanking are available. Floating blanking allows a set of number of beams in the sensing field to be disabled. For example, an unbinding a roll of steel where the steel plate can change its height when the diameter of the roll changes. So that's the upper picture. And then fixed blanking allows a selected number of beams to be disabled. Not all beams need to be disabled when material crosses the light curtain. But be aware that any blanking of light curtain beams will increase your resolution, and that has later on an impact in your distance calculation. Now about safety controllers. So light curtains, they can be connected to the safety controller, and safety controllers, they also come in multiple flavors. And within the configurable ones, there are software muting blocks. So safety controllers can also take some functionality so that you can actually then do the muting setup in your safety controller, and the connection to remote I/O blocks. So here you see the light curtains connected to one block, the muting sensors, possibly another e-stop, or another light curtain and safety interlock switch. So this can provide also an economical solution. Installation of these devices. Well, you've got to be very careful and follow always the manufacturer's instructions. So avoid the possibility to reach behind. That means by reaching over, reaching under, or reaching around. Also avoid the possibility to stand behind, so between the ESPE and the hazard area, or it's accessible from behind. Installation. Prefer to have a fixed, sturdy installation of these devices. Align properly using an alignment tool. Use special fasteners. Protect against mechanical impact. There are certain columns available that can protect the light curtain against impact. And of course, always follow the manufacturer's operating and installation instructions. Also, if you have multiple light curtains arranged next to each other, like it's depicted here, then watch out for the cross-reference or influence. And there are light curtains out there now, they are coded, and they can actually counteract that and have no interference. That depends on the manufacturers and the specifications. Now we come to a point where it's about presence sensing. So if there's a work cell area around the machine where a person could hide behind some equipment, and you don't want somebody to close the door, and so you can use presence sensing devices like a light curtain, two-dimensional area scanner, or the three-dimensional camera, so that you cannot start up and reset and start up the cell while somebody is in the cell. Also some observations from the field. So some issues with light curtains that you could come across. So for example, safety distance could be incorrect. So the safety light curtain was conveniently mounted on a machine frame or structure without calculating the machine distance correctly. Or we have the possibility to reach around, over, under, and stand behind the light curtain undetected. And incorrect selection and installation of the light curtain. So this could be the wrong type, resolution, the length of the sensing field, environmental factors, mechanical protection, dust and debris, and the like. Or a safety light curtain, hopefully it is not, could also be disabled on a machine, or can be tampered or manipulated with. Lack of maintenance, also an observation, and of course, test the safety light curtain functions very often. Now we come to the subject of safety distance calculation with ISO 13855. So there are different approach to the protective device. We have a normal approach, we have an angled approach, and we have a parallel approach. So here I'm going to talk about one case, which is the normal approach, a person walking up to the protective device. And here in general, some of the formulas, or formula here is S equals K times T plus C. And the direction of the approach, as said, is normal. So K stands for the approach speed in millimeter per second. S is our minimum distance to the danger point. The time T is comprised of two factors here. Is the ESPE time plus the control time and the mechanics. And the factor C there is additional distance dependent on design and installation. And also there's excellent guidance in the IEC-TS 62046. Now we're going to fill in the blanks with the definitions. So the approach speed K, approach speeds in ISO 13855 is 2000 millimeter per second for normal unhurried reaching with upper limbs, 1600 millimeter per second for normal walking. But have in mind, depending on the application, it can be necessary to take into account higher speeds, for example, attempting to adjust the part, using bicycles in the vicinity, foreseeable reasons for running towards the machine, and the like. And within the calculation, also our resolution is a factor. So we touched on this, resolution D, 40 millimeters for finger, 30 millimeters for hand, and larger than 40 millimeters for the protection. Then we're going to touch on the machine stop time. So here's a diagram, machine speed over time. And so on the left, we have a column starts with the detection of a person, then our presence sensing response time. Then we have the machine control response time. We have the machine deceleration until the machine stops. So this is our overall time T. So now we're going to do an example here. So we have the approach is normal, the ESPE type 4, resolution D is 30 millimeters. The total time is measured, including the ESPE, everything together, is 150 milliseconds. And the safety distance on the machine, on the label, it's written, it is 400 millimeters. And now we're going to check if that is sufficient. Now, because we have a minimum of 100 millimeters, then we are less than 500. We have to go to an approach speed of 2000 millimeter per second. So we fill in the blanks here. So we have S equals K times T plus C. So S is the 2000 millimeter per second times the total time. And here comes our resolution into play in the factor C. So we have a total result of 378 millimeters. And the label says it's 400. So in our example, the distance is sufficient. Now, when you look at other calculations or formulas, you find calculations according to OSHA, where the distance is 63 times the total time. So 63 inches per second is that speed. But that's depending on the application or type of machine. Also calculations to ANSI, where the distance is also with the factor K. And then you have, depending on the machine and the devices that are installed, and cause a delay time. So you have lots of timing factors to consider. Plus the factor C here is the depth penetration. And the depth penetration formula is on the bottom of that slide, where QS equals the light curtain resolution. But now we got to look at also when our light curtain is the protective device, we got to make sure that we don't run into any reach over situation. So in this example, we have the light curtain. The size length is fairly low, and we have the height like just a meter, like 3.3 feet. Resolution 40 millimeter. Total time is 125 milliseconds. Safety distance on the label is 1,000 millimeters. So now is this sufficient or not? So we punch in our formula, and we will get the overall result of 200 millimeter, but we have this 1600 millimeter approach. 500 millimeter is the minimum anyway, but the label says 1,000. So 500 versus 1,000, are we still good? But here we have a reach over situation. So you have in the table in the standard gives you the measurements, and if there are protected structures that are less than 55 inches, they should not be used without additional safeguarding. So I want to point out, point 1 is the electrosensitive protective equipment. 2 is our hazard zone. 3 is the reference plane, like the floor. And there are the 2 factors now, A and B, height of the hazard zone, and B, height of the upper edge of the detection zone. And then we got to see if we need a correction factor to be further away so that the person cannot reach over the light curtain and reach into the hazard zone. So we go in our table in ISO 13855. So we have the height of the hazard zone, the factor A is 1,000 millimeter, and the height of the upper edge of the detection zone is also 1,000 millimeter. So, and where these 2 numbers cross, we have a correction factor of 1150 millimeters. So overall, the safety distance, our label says 1,000, so we have to add to the 200 millimeters that was calculated, we have to add 1150 millimeter to that equation. So our overall distance now becomes 1,350 millimeters. So that the label info and the distance was not correct. I'm going to touch on safety laser scanners. So they can be used for area guarding. They have the warning and protection zone. And here's depicted is red is the protective field, and yellow is the warning field. And depending on the manufacturer, they can vary in sizes how you can configure those. Using an area scanner on a work cell is definitely one way to go for area protection in front of the work cell, or also inside the work cell for presence sensing, so the multiple uses. Or you see even mounted as over a door opening. So that's another way to use these devices. Now, not going too much into details in calculation, but in the standard, you also have calculation examples and distances that are applicable for the laser scanner. So there is, on the left, you have the laser scanner mounted very close to floor level in a certain distance and the height. And then you have, in the middle, you have the laser scanner mounted higher up in the distance. And in the right one, you have the laser scanner mounted at an angle at a certain height. And all these cases have the formulas and the information you find in the ISO TS 62064 provides excellent guidance for that. Now, any system needs a validation. So in the calculation, we saw that the time factor is always needed. So validation tools and methods. So validation of a presence sensing installation requires two parts: evaluation of installation to comply with installation requirements and ensure that the PSD cannot be manipulated. And then, of course, confirmation of the safe distance, measure actual stop time, calculate the required safe distance, and compare to actual. So there is two methods. One can be an encoder method with specific hardware and a computer plus the software and the like. So that's one way of doing it. Or a more practical use would be the video camera method. So you take a video of the machine during a stop event, and includes the state of the safeguarding device initiating the stop signal, and then you analyze the event frame by frame to calculate the stopping time. So, for example, a standard movie clip is taken at 30 frames per second. Depending on the recording device, frames per second can also vary up to 240 frames per second, depending on the device, for example, smartphones. But you got to find out what your frames per second are. So 30 frames per second would provide a 33.3 millimeter time increment. Digital cameras are capable of making movie clips as our digital camcorder. Then use a tripod and use video analysis software. So basically, this is the software that will play that video and give you the specific frames per second that you need for the count. Now, what steps do we need to take? So we need to determine the hazard location, measure current safety distance, determine the critical machine motion and high speed, select the camera view, do the video stop event, analyze video frame by frame, determine depth penetration based on presence sensing device and installation, calculate required safe distance, and compare to the current one. So here we saw this graphic before. We have the detection of the person, we have the response time of the PSD device, and then machine control, response time, machine deceleration until the machine is stopped. So we take a video and we have a stop event, LED, red LED on between 0 and 1, and we reach 0 speed between frames 7 and 8, so the count here would be 8. Then we have to look at the facts. So basically the red LED was first noticed in frame 1, therefore the stop event happens between frame 0 and 1, and the machine shows no relative movement between frame 8 and 9. Therefore, 0 speed was reached between 7 and 8. The PSD LED comes on after presence sensing device response time, so we have to add it to our time measurement. So when we do the video, take several videos, be sure the presence sensing device status, so the LED, they are visible within that movie. Apply marks to the machine and then show frame by frame. So when we do the calculation, so in this example we took multiple takes and we came up with 4 different frame counts, so 19, 20, 20, 21. So we do an average, so about 20 frames we needed until the stop was achieved, and so 20 frames by 30 seconds per frame is the time of 0.67 seconds. We add the correction time for the presence sensing device, which is another 20 milliseconds. So we have the overall time here of 0.690 seconds. We plugged it in our formula. So we use the approach speed with 2000 millimeter per second. We have the factor C. We have our time t that we measured with the video and the frames. So and we have the resolution, and then we plug this all in. But because we are greater at 500 millimeters, and in that table in the presentation before, now we can use the approach speed of 1600 millimeter per second. So overall safety distance, for example, could be 1312 millimeters. Now we can talk about, and that's the optoelectronic device selections. So a couple hints. So to consider when selecting optoelectronic devices. So of course, does the application call for such device? So when you remember, we go back to our machinery life cycle, and when our concept, calls for this, and then our design. So does a risk assessment exist? We just touched on that. What type of safety function needs to be accommodated? What type of safety device is used to address the safety function? So here is, of course, all the different types that we have, all the resolution, length of sensing field, is muting needed, what performance level required is available, are appropriate safety controls specified, did we consider environmental factors, IP rating and the like, and possibly more. All right, that would conclude the presentation section. And yeah, now there would be some time for questions. Thank you very much.
All right, thank you, Thomas. That was a tremendous presentation, very comprehensive as well. Before we jump into the questions, let me just ask everybody to take a moment to complete the feedback form that you'll see in the lower toolbar. So let me shift my screen over to get to some questions. First question, Thomas, what are you detailing for calculating stop time by video footage? Is this detailed in an ISO or ANSI specification?
Yeah, I would say this is one of many methods. I think you have to come up with a time, and that's the most practical solution to go about it. So the standard calls for you have to put the time in, and that's one of the methods. That's what I can say.
Okay, thank you. And let me just point out to everybody, please feel free to send in any questions, and we'll forward them all on to Thomas if we don't get a chance to get to all of them. We'll try to not ask really specific questions that might be of only interest to one or two people, but we'll get to all the good general questions. And if you have something that you want to get clarification on or more information on, this would be your chance. So let me see some of the other questions. Okay, here's a question. How important is the alignment of the light curtains?
Oh yeah, this is obviously very important, and even if I say obviously in the installation phase, depending on the distance between the emitter and receiver unit, it can be difficult to align, but there are tools out there that help you with that. For example, alignment tools that will help you get the light curtain aligned and function properly. Also, going back to that other question, I can do a little research and find out if that method is written down in a standard, but to my recollection right now, I have not seen this, but the time measurement definitely is a necessity, and that's one of the multiple methods to achieve that.
Okay, thank you. Another question. The question is, what do I use when space is at a premium in my plant or facility? What would you recommend that they use?
Right. So in this case, if space is at a premium, it really needs to be decided on what need to be protected, what kind of resolution of the light curtain you need. Depending on the resolution, you have to be a certain distance away, and sometimes you need to accommodate certain distances, and sometimes it's tough, or you have to go to a different technology. But when you need to protect a finger and hand, then certain distances are required, and there's no way other way about it.
Okay. This is kind of a big question, but the question is, which option is the best to use overall, if there's such a answer to that question?
Yeah. The best option overall, well, of course, the short answer, depending on application, but it could also be a combination of devices, or safeguarding. So it could be hard guarding, it could be movable guards, and could be guarding via optoelectronic devices. So that can also be a mix. It really is dependent on how personnel approaches the machine and can approach the hazard area and how to protect it against.
Okay. Question just came in. Can you elaborate more about the safety radar? And he's saying not the 2D scanner. He wants to know just more about the safety radar that you talked about.
Yes, and let's just go to that. That's a new technology that is out there, and radar. I mean, commonly known as it will detect metal objects. And it's known from from the aerospace industry. But as far as I know, the area or the radar scanner works in a different frequency level, in the gigahertz level, and with special algorithms that the manufacturer provides, it can detect, so it's good for body protection, can detect persons as well. And I have some information here. And it can be mounted horizontally and vertically, and it has a distance of 4 meters. And you have you can angle the device too. Let me just push this picture here. So we're talking about this device that is in gray, and so you can swivel that as it's shown up and down, or you can mount it in other ways. And the length is 4 meter in range, and it, like I said, it works on a higher gigahertz level, and it can protect human beings. So that's a new form, and what that also is, it's good to be used if the factor of debris, dust, sawdust, maybe water droplets, or other things that could cause what we call nuisance trips of other optoelectronic devices. So this might be another alternative to be used. So that's pretty new on the market.
Okay, thank you. Let's see. Is it configurable like a scanner for the determination of the zone?
Yes, it is configurable. Yes, some manufacturers they provide software and a controller with that unit, and it can be configured. Like in general, almost like a two-dimensional area scanner. Yes.
Okay. Another question: can 3D cameras be used to allow access to an area with mobile equipment, but stop when pedestrians enter the area?
Actually, yes. Let me rephrase that. Yes, and partially no. On that 3D rated camera system, and again, it's all dependent, and I hate to say it, on the application, but when I go into this slide, the three-dimensional view. So you have this pyramid view, and then you have the zones. So there can be cut-out zones. They can be configured via the software, so that you can get processed through. But you also have to make sure that not personnel can sneak into that opening as well. So you got to have other means. So yes, you can have material and exit and enter, but you also have to make sure that you do not provide access to a human, to personnel. So for example, in this picture here, we have the conveyor, left and right and in the front. So of course, that is something, and so there we can create cutouts. So sometimes you may have to, consider some additional guarding. So sometimes one device, may not fit all necessary requirements that you would like.
Okay. Actually, I'm going to ask you to do a favor for some of the people in the audience who are listening to the webinar. They asked for your contact information, so I know you've flipped back to show some other slides, but okay, there you go. Yes. So those of you who'd like to contact Thomas directly, all his contact information is right there. And I'll give one more call to the audience. If you would like to ask Thomas a question during this live portion of the webinar, please feel free to do so. You certainly can contact him on the information that you see on that screen there as well. And let me just ask everybody that if you did register for this webinar as a group, so there's more than one of you participating today, please add the names and emails of everybody who was in attendance on the exit survey. So I think that looks like it might be it for the questions, at least for now. You may be getting some more questions offline, Thomas, but for the live portion, it looks like that's it. So let me once again thank you, Thomas Hartig, and our sponsor, Pills Automation Safety, for what was just a fascinating and very interesting webinar today on some of the technologies that are helping keep our workplaces safer. So on behalf of EHS today, and again thanking Thomas and Pills, I'm Dave Blanchard. Thanks so much.
Thank you.